So first, I'm going to say thank you to Dave and Mark for referencing our project several times in their presentation. The word path has come up quite a few times, so I appreciate that. It's a nice little intro. So our project is essentially around using floating car data to analyze signal performance. Signals is obviously a very hot topic at the moment. There's a lot of people talking about it in the room. Signal timing data. Hopefully, we can kind of help with part of that. I think we are part of the story, and even Mark, you mentioned it a minute ago. I think the three projects today complement each other quite nicely. So I think there's a good running theme throughout it. So what I'm going to talk about, background of the PATH project. So Andy's going to give a little bit of a background around the team, the research that we undertook, and some high-level information about the product development. I'm then going to talk about project features. So I'm going to show you several slides around what we've actually developed, the concept itself, oh, this is on a timer, that's going to be annoying. I don't know how to pause this. I'll have to keep going back. So yeah, I'll show you some of the project features. And then actually what I'm going to focus on most of the presentation about is the next steps. So since the project finished a few months ago, we've done quite a significant amount of work about how we're going to bring this to market and actually productize it and make it available to the likes of many local authorities. And I'm going to showcase kind of what we've done so far. And then finally, there is a little plug for the Traffic Signal Maintenance Fund, which Darren is obviously the sponsor of, and some of the local authorities we're also working with on that. So, Andy.
Okay, so I'll talk about the background to the project. So the first thing, just to remind you all that these three projects were both funded, or all funded by Small Business Research Initiative. But the key request from DFT was to produce some products that local authorities could use. Not just do more research that says, here's a research project and can we have more money to do more research? We've got to come up with something that's deliverable. But also we had to work with local authorities. So our challenge was about signals, and it's not just about fixed signals. We can do temporary signals as well, Steve, and we can do signalised roundabouts, and we could do junctions that ought to have signals. So the idea was to try and examine corridors and junctions and turn performance. Do you want to fix that now?
Yeah.
And I'll keep talking.
You keep talking.
So basically, you all know why you want to modify and monitor what's going on in signals, so you can produce better plans. And we just heard some of them from the 1970s. So you can understand responses to questions from members. You can understand, for example, whether temporary works are causing congestion, as we just said. But also we can understand where you might want to do some maintenance, where you want to spend some money, you might want to put in some more sensors, you might want to do something different. So in other words, how to prioritise your spend. And also in the forthcoming priority in terms of Darren's maintenance fund, did you actually make any difference? Because what we'd like to be able to show is that giving money for the maintenance of traffic signals reduces congestion, and therefore DFT should have more money for the maintenance of traffic signals so it can reduce more congestion. So that's one of the reasons why we wanted to do the project we did. So we used INRIX's anonymised floating vehicle data. So many of you will have seen the kind of aggregated journey times that INRIX and other people do. What we're going to look at in this project is individual vehicles. So this is a blob, as David so well described it, moving along, rather than it's been processed and anonymised. And then we do analysis on that to look at individual delays of vehicles and signals. And the reason we can do that is because we've got so many blobs moving around that have got a big piece of kit on them. And thanks to BODs, we've got big red, blue and green things that move around called buses as well, about later. And this is only going to get more and more connected. And this afternoon after lunch, we'll show you some of the stuff that we're all doing in terms of connectivity into the vehicle. If you're putting messages into the vehicle, you can get data out of it as well. And the key thing was that we found very early on when we were talking to local authorities that one size doesn't fit all. So Steve's got some experience with TfL. There are smaller authorities at the other end of the spectrum and all in between. So you'll see the other projects kind of focused on one key user. We had a key user in the City of York, so thanks very much, Dave and your team. But we also had a load of other smaller local authorities that we did iteratively to get some testing. And if the right slide works. So City of York were the kind of prime users. Sean and his operation team were very helpful. But we also had a whole logo test of other people. So many thanks to all of you who are in the room. Some of you we've never actually seen in 3 dimensions, you've only seen you in 2. But just a shout out to the technical team. So Peter Routledge would have been here today. He's our local hero on signals. His family's got COVID, so he won't be today. John did much of the IT planning. Neil, where are you, Neil? Neil at the back did much of the technical stuff on traffic signal timing. And a guy called Sanjit Samadar from the City of York did all of the user experience stuff, which I won't repeat. Dave did a much better explanation of it. He can't be here today because he's in the university teaching students how to do proper user experience of stuff. And I think that was one of the, echoing what Dave says, one of the key things in terms of meeting requirements of the project was to have someone who didn't know anything about traffic involved, but asked fundamental questions. Why do you do it this way? And then helped us with the local authorities. So what did we do? We did some user requirements in the way that Dave explained it. A lot of collaboration with City of York. We then tested things out online with focus groups of local authorities and said, I don't like it that way, or can you do it that way? And lots of questions to make sure that we didn't just make one tool that fitted one user. The main themes that we got were lots of people have lots of different ways of doing lots of different things, but it all boils down to, can you compare historic data with what's going on now? There's a real difficulty in determining whether an intervention has made any difference, be it manual or automatic, as we said. And local authorities want something that will help them be proactive rather than react after the case. We've just discussed that in terms of traffic management plans. But also this idea of zooming in. So we have data that you can have for the City of York, and we can zoom in to that junction down there. And the reason for that is you never know when the impact widens out. So you can look at a junction, you can look at a corridor, you then need to look at a network. Is that the A64 around the network? So that zooming in is something we'll focus on. So there's three themes to it. The first is the data. Dave's done a very good explanation of that. Productized high-frequency data that comes from individual connected vehicles. So it's not been anonymized. So it has been anonymized and not been aggregated. So you can still see the individual. And that snaps to an open source map. We use OpenStreetMap because it's free and it's good. And if you have changed your network, you can go and edit it yourself. And it's a good way to get a good route trip. Then we developed a whole load of metrics, thanks to Neil and the users, which are ways to determine the travel time of a vehicle through a junction. And that's not just through a junction, that could be a turning move of the junction as well. And then we've also looked at things such as stop times and splits and so on. So what we did was we developed a whole load of tools. Now, we did do a webinar on all those tools a few months ago. We're not going to repeat all that. But in essence, we have developed corridors that you can use to look at the performance and then zoom in right down to turning move level. And the thing is, because it's data that's in the cloud, you don't have to go outside to do any setting up. So we've done a whole survey of many of the local authorities without ever actually going there, without ever actually meeting the people involved. It's all been done. And then we've summarized and reported some metrics in a way that we hope might help Dave's modeling, but also you operationally. I'm now going to hand over to Dec, if I'm Ant, and we'll hear about the project.
Thanks, Andy. So yeah, the theme really is to save time. Really, that's what we're trying to do. So the product in itself is obviously about reducing congestion, emissions, and all those good, all that good stuff. It's really about saving the engineers time that's kind of got to go out and understand that traffic signal estate. Again, I'm referencing Dave's presentation here. He showed you all the traditional ways that you'd gather that information with clicking counters, counting cars, all that sort of stuff. We need to stop doing that. That shouldn't really exist anymore. We've got better ways of doing it. That's what this project's really about. So this concept of zooming in, identifying corridors, what we've done is essentially start with this corridor approach. So it's identifying your corridor in theme with a UTC scoop region. So a user would draw a corridor through a road network, and then what we would do is then start producing an associated heat map with that, and understanding how those vehicle journey times travel through that corridor. So once you've defined the corridor, we can then produce all the underlying metrics. And then going down even further, we've got something called the curtain bead diagram. Now, curtain bead diagram came from Andy.
It reminded John of his grandma's curtain bead in his kitchen. Those of us of a certain generation used to have these curtains that were beads that were on stream,
Right.
1970s.
Probably makes sense when I show the slide a little
Yeah.
bit later. But so the curtain bead diagram is idea that you can see the individual trip movements through that corridor, and you can see the irregularities throughout that corridor from each of those trips. And the irregularities are essentially showing up things like the delay and the stop time at each of the junctions as they go through that corridor. And then finally, the most granular view at this zooming in level is individual junction views. So we get right down to the individual junction to see what's the performance of those traffic signals and how people are moving through it. So this is the corridor view. Essentially what a user would do is they'd create their corridor from A to B. It doesn't have to be an associated scoop region corridor or anything like that. You can create it wherever you want. And then what we do is then pull through all the underlying OSM junction data, so you can see all the signals throughout that corridor. And then we then also use the underlying trip data that we have against that corridor and map it. So apologies for those that probably can't quite see in the back, but you can see the thickness of the line there associated with delay. So using our travel time data and our trip-based data, we can map that against that corridor to understand how they're traveling through, and the thickness of the line denotes the amount of delay associated with that corridor. The great thing about this is really identifying the pinch points. So quite quickly, you can see that somewhere halfway through that junction, roughly that halfway through that corridor, there's an excessive amount of delay at the beginning and then even down to the end. So perhaps what the user may want to go do is create a further corridor to see how it goes throughout the rest of this road network. This is actually specifically in York, and so thanks to James for identifying these corridors and letting us use these as the examples. Okay, so how that actually is calculated is essentially this screen. So this is the heat map. So this is all the underlying data. And what we do with this is essentially use I mentioned our trip data, which has baseline speeds against links. So each of the links along that road network will have a baseline speed, and then we'll use the actual speeds from real vehicles and compare that. And that's essentially this data here. So we're providing that heat map view so someone can quickly see where their most problematic areas are. We then also break that out in time of day. So you can see the AM, the inter peaks, the PM peaks. So on the left here, which is the before screen, you can see in the AM peak, the dark purple there is associated with the most significant delay. So that part of the route network has heavy delay in the morning. So that's probably the area that you want to go and focus your retiming efforts on. Finally, we also do, again, apologies, you probably can't see it on the screen, there's also sample size. So that's really for context. So sample size is really important to understand whether you've got high penetration, low penetration. So we also do provide the sample size so the user can make a decision to say, okay, well, that's actually a low sample size, so maybe I want to treat that slightly differently, as opposed to a high sample size where you can see the majority of those vehicles having that same issue. So just a little bit of background about how we actually do this, and some clarity about how the vehicles move through the junction. So firstly, what the most important thing is, we actually need high fidelity and high frequency data. Frequency is really important because without the frequency, you can't actually understand the vehicle movements. If you're only having slow 30-second individual waypoints traveling through it, it's much more difficult to understand how that vehicle goes through that road network. So increased frequency is really, really important. So this example that I'm showing, you can see there's two vehicles. The yellow line here, which is actually a vehicle that's traveled through, again, a junction in York, I'm showing it for illustrative purposes. The waypoints that we're dropping here, which are the associated breadcrumbs, you can see that the difference between each of those waypoints is fairly regular. The distance between them, they're dropping at fairly regular points, and therefore the associated speed as they travel through that is also fairly regular. So they're keeping consistent speed. So this vehicle in particular went through this junction without being stopped and carried all the way through. So pretty much got through that traffic signal on green without having to wait at all. Then you've got the left-hand turn, and then you can see the differences between those. So this left-hand turn vehicle, again, starts consistent in the first blue dots, keeps a fairly steady speed up to the junction, And then, as you'd expect, before he turns left, there's much more slower movement. Perhaps he had to wait for a vehicle before he turns left. There was slow going around that corner. He then travels around that corner and then carries on back up to speed. So that's kind of the premise of how we can understand how a vehicle moves through that junction. So here's the famous curtain bead diagrams that we were talking about. So how we actually map that data is this. So what we're showing here is actually the same corridor that I showed earlier that I referenced. And this is essentially a time-space diagram. So distance as you travel through the road network going down, the little graph there, and then time as you come across over to the right here. So mapped also on the left-hand side, which are the black lines there, actually the individual junctions. So that's the traffic signal junctions working through that road network. And then the color of each of those lines denotes an individual day. So, and these I would also say are complete journeys. So what we've done is pulled out all the whole journeys that have gone that entire route and then mapped it against it to understand how it's traveled through that. So quite quickly in this one, you can see that roughly around the blue line, that's kind of where you see that the vehicle starts slowing down. There's an increase in the amount of time that they move to the right. But then specifically, we can pull out quite quickly there, highlighted in the red circle, a vehicle was stopped for a prolonged period at that junction. So it may be just a one-off, but the important thing is it gives the information to the engineer to say what is actually happening at that junction. I need to go and have a look at it. It happened on a Tuesday, by the looks of it, based on the day. So goes back in to see what actually happened on that Tuesday. Is that something I'm seeing regularly? Is it always every Tuesday that I see that? Or is it just it's a one-time event? Now, if it's regular, they would then do something with that information, is go and retime perhaps their signals for that specific Tuesday. They need to understand why that's happening. So they're the key things that we've developed as part of Path. But Path has really enabled us to understand what's needed to build a signals product or an analytical product that analyzes signals. It's given us a lot of learnings around the user needs and the value that it actually brings to the user. For some of the lessons learned and obviously the limitations that are within the data set, and then the complementary products which Dave and Mark equally have, kind of help build that complete picture. So mentioned in the SBRI requirements, we have to actually productize this and make it a scalable product. Now, the prototype that John helped put together is currently not as scalable, so we need to move that forward into the INRIX suite, as we would call it, how we can make it scalable across the entirety of any local authority that may want to get access to this. So we've now got a team of people working on developing and bringing in the insights that we have from the Path product and integrating that into what we're calling signal analytics, INRIX signal analytics. We have started this process, and what I'm going to do is just briefly go over kind of the key features around that and then the usability. So one of the main user cases and requirements that came out from Path was actually having a quick view of the road network. So a corridor is obviously a focused area. It's now about how can we kind of bring that data at an even higher level to say, what is my entirety of my road network? What is the entirety of my traffic signal state currently saying? So we've created this dashboard view. And this dashboard view is essentially broken up in a couple of different things. So on the left-hand side there, the idea is that every single traffic signal that's in your estate, you can plug into this, and we would start monitoring it in the same metrics and aspects that I referenced earlier. And then we would, week over week, day over day, be able to compare how that's changing. We will then also tag what we call a level of service, which is in the bottom left-hand corner of the screen. And then you can see quite quickly which ones are performing well, which ones aren't performing as so well. And then finally, in the center there, that's actually how they're changing day over day. So which are my top worst performing signal junctions, and then which are my top worst performing corridors. So if a signal engineer comes in the morning, they can log into this system, and it would just update automatically, and they'd be able to see that reflection. So hiding behind the dashboard is this, which is the network-wide view. So this is using that same grading structure. It's kind of like the concept of the heat map, which people quite like, is understanding where I need to focus my efforts. So on the left-hand side, the very left-hand, you can see a little cluster of traffic signals there. They're actually yellow, denoting that perhaps there's something wrong with that region. So it's a quick reference look before you dive into the detail. So that loaded there. So in Path, we were able to calculate observed speeds against the baseline, and that's really important because speeds is actually related to how the vehicle drives through a junction and their associated travel time. I'm just going to skip through these. There we go. So as this example here, what we essentially do behind the scenes is we track a vehicle as it comes inbound to the signal junction. So on the far left-hand side there, the node, the center point based off OSM. As that vehicle comes into that junction, we then see its associated speed and reference it against the reference travel time. So the free flow speed, so to speak, as you go through that junction. So the hollow lines, the hollow dots as you go through, are what a vehicle should travel through that junction as if it wasn't going to stop. And then the blue dots are what the vehicle actually did. And then the difference between that is something that we call delay. So you have the reference travel time through the junction and then the associated delay that that vehicle had seen going through it. Much like the curtain B diagram, you can see that there's the stop area there. So taking the metrics a little bit further from delay, it's one of the metrics. What we also want to start looking at is things like arrival on green, arrival on red, and also split failures. So arrival on green, for example, we've already just explained about it. You've just went straight through the junction. We can see that there's a nice smooth transition. Arrival on red, that example where you see the dots suddenly flatline and it's waiting at that traffic signal junction. It then gets a green light and the vehicle carry on going through. And then split failures are where they've had to wait for more than one cycle, which is obviously really important in the traffic signal world. No one really wants to be waiting more than one cycle. Roughly 100-second cycle time. If you're waiting longer than that, anyone will know that it's very frustrating and also causes severe congestion and a knock-on effect. So clicking on one of those junctions then brings up this junction view that I referenced a little bit earlier. And what you can actually see is each of the approaches. So the left hands, the right hands, the aheads, we split that junction up into all the possible movements that it can make. And the on-screen example, you can actually see that the northbound approach was the worst delay across all three of those movements. So that's probably where the signal engineer needs to focus its time and efforts to say, how can I improve the throughput of the vehicles through the northbound approach? On the reverse of this, perhaps this is a minor road and the signal engineer is happy with that because they want to penalise that road for a certain reason. But at least it gives you the evidence to understand what that effect is. So when you click on each of those movements, we also then break down the metrics that I mentioned earlier: arrival on green, stop count, split failures. So if I click on a single movement there, it will give you all of the associated data and metrics with that. And you can see over time of day, so there's a top in the bottom right hand corner here, start at midnight all the way through to the following day. And you can see how many people are getting through on green or not. And particularly in the middle here, so roughly around about 10 AM, perhaps that scoop cycle changes or the timing plan changes within the UTC. And you can see that a lot of people are actually getting stopped on red there. There are very few people getting through on green. So again, that may be the point that you want to focus on retiming. So it's not just about identifying which route it is or which movement it is. It's also about roughly what time of day are we seeing this effect. And most importantly, the premise of this project and this platform is to compare. It's okay, what do I do with this information? Have I actually improved anything? And this is really what the platform's about. So it's about taking and understanding and prioritizing your network your road network. Once you've identified those issues, you can then go in, retime, reprioritize, and then how is that actually changed? So in this example, you can see that there's a PM peak issue. They've retimed, reprioritized, and you can see that the metrics have improved. So the number of vehicles associated roughly the same there, but the average control delay has gone down from 34 seconds down to 18 seconds, which is quite a significant amount of time. So then finally, how we kind of align with the Traffic Signals Maintenance Fund. So a brief reference to this from Darren and the team. So it's understood that within the Traffic Signals Maintenance Fund, which I know some of you are here today and I've been discussing it specifically with, you're required to provide evidence against the 7 themes that have been put together by the fund. Well, thanks to the SBRI funding and in particular DFT, we do think that PATH can help with some of those, specifically around themes 2, 3, and 4. And 2, 3, and 4 are actually associated with prioritizing your upgrade network, reducing the amount of emissions, and actually providing a monitoring mechanism. So it's not just about doing this once, it's how do I monitor this consistently over time. So PATH is a platform, the future, sorry. So in a matter of months, sorry, I have to say PATH, the current platform that is available, it's a product that we can use now. It does take a little bit more setting up and effort and things like that. But as we move and transition that into signal analytics, it becomes a scalable product. And we're only a matter of months away from completing that integration work. So the screenshots that I've shown you today are actually just the kind of subset and the initial screens of that. We're expecting it later this year, potentially early next year. We should hopefully then move into a fully fledged product that we can make available to the market. And then PATH signal analytics product can be helped to prioritize your upgrades in your traffic signal maintenance fund. So it's a very, very quick summary at the end here. Some of the key use cases we think as part of this project. You can view your junction performance every day. You can drill down into movements causing individual movements that are causing issues. You can identify the junction performance and categorize. You can see your level of service at each of those junctions and the associated values. You can run reports and actually get emails of those reports, analyze your before and after studies and actually evidence it, and then most importantly, reduce the amount of time that an engineer needs to go out on sites and analyze a junction. They can do this in a matter of minutes as opposed to a matter of days or weeks that was previously done. Roughly half an hour, so that's me.
Well, we don't have that many, so I'm just going to shout. Questions? We've got just over 10 minutes.
Sure.
Actually, so I can see you. I've got 1, 4, and 5.
All right. What is your aggregation level, sample rate, and what you do when the sample rate is very low? For instance, have one vehicle that might be in one cycle, and therefore might have very high delay.
Yeah, so sample size is important, and that's part of the effort that we're doing now to try and increase the amount of sample size. And as I mentioned, fidelity and the frequency of that data is really important. So we're actually looking at how we can bring more data sources on to increase that, and that's part of the transition process that we're going through. But within the platform itself, if we don't see enough sample size, we actually don't show it.
Okay.
So I think in the before and after one that I showed previously, so there was a couple of dashes. That's actually us saying that we don't have enough sample size specifically for that movement, so therefore we won't show it. So we only show data that we are confident in.
Okay. So those 3. Yeah, number 2. Yeah. Thank you for your presentation. Just a couple of points here, I suppose. Turning some of the last discussion, last speak on its head. Do you think we're getting close to a point where we could actually tell people what the predicted delays are going to be? So therefore, what is the performance on lengths of our network? And secondary bit to that is we're very focused on traffic signals, appreciate why, but again, can we use that type of system to not just control throughput at signalised junctions, but at say roundabout junctions by controlling the amount of delay people get when they get to a roundabout.
Yeah, so short answer for both is yes and yes. So that's partly the reason why, and as Dave highlighted, so to your first question, we think that there's quite a good partnership between the INRIX and IMETS. They are great at doing simulation and understanding what potentially could be and running those different scenarios through. I think that's really where the IMETS guys add significant value. We are looking at how successful have those interventions been. So to your first point, and your second question, sorry, was
It's about then how do we integrate signal junctions with roundabouts?
so yeah, roundabouts are a very difficult thing to deal with, and actually we're kind of unique in the UK, I think, in terms of having signalized roundabouts. It doesn't really happen, certainly, in the States and even over in Germany and things like that. They don't really have signalized roundabouts. It doesn't exist. But the platform itself, yes, should be able to do that. We'll be able to do signalized roundabouts for sure, but there's no reason why we couldn't also look at non-signalized roundabouts. It's just kind of a mapping exercise that we would need to do. Sorry.
Yeah, it's wherever you have effectively a node that you're interested in. OpenStreetMap allows you to edit the map. So if you're interested in a priority junction, put a point in there, and then we can analyze that. If you're interested in a set of temporary traffic signals, hopefully there might be a point there. So although we focused on signals, that's because it was, I want to say, low-hanging fruit, but that was a priority. But we found that with the openness and scalability, we could look at anything.
But equally, it's the quickest way to implement interventions. If you're looking at a non-signalized junction, it's going to require much more significant amount of investment and work to make a change to that, likely road layout or something like that.
Or signalizing it.
Or signalizing it, putting signals on it, yeah, for example. While as traffic signals, you can actually make interventions quite quickly and have a very positive impact on the road network quickly.
Okay, thanks.
Yes, I think that on the first one about the data quality. One we were really participating. So one got out of this with the data set provided us where which area, which we were great. It's really exciting stuff. When we looked at it, over 95% of the data actually a big personal strategic phone network, route going in and out for this area. Took that out, left actually wasn't that much. And I'm quite a feedback into an AI model wasn't sufficient enough to provide us with data. I think one of the challenges for that urban traffic, how we understand those things, I think obviously a really good start, starting to see that, but you could put it on their sat navs and providing information on their strategic journeys, they're all to school the local youth, sure that they are.
Yeah, so as I mentioned, that the increase in fidelity and frequency of data is something that we're working on now to increase that amount of data. But actually, the specific data that you're referring to, Paul, is actually a subset of what we provided. So the data that you've got as part of the project was just specifically for the corridor that you identified. So there is a vast amount of data associated with either side of that. It's just that that is a very, very small extract, just to be clear.
Okay, thank you. And number 4.
Yes, it's Tim Raven. Teams.
Yeah.
Great analysis tool. It can tell you where you've got common prevention. And I guess it's much yeah, but you do next door. What about recommendations now? Travel Thursday morning and absolutely brilliant about this area, which is when what do I actually do? Where will the system really start to say, Tim, if I were you at this?
Yeah, so I think the complexities with that is, and one of the things that we recognise is signal data. I think we've spoken about it a few times and referenced it down here about standardising it. We know that traffic signal data from timing signals is really, really important and it has value in it. I think where we could potentially start making those recommendations is once we're able to get access to that data, but it's not available at this stage. So whilst we're kind of just providing one view of what the road network is, we could dive deeper into that rabbit hole if we had access to that data, but we don't. So the way that we have to do that is partner with companies like the Meds who could run those simulations and potentially outturn signal timing plans to say you should operate it in this way. So there's definitely value in it. It's just we need that data to be out there. Sorry, go on, Andy.
I think it's really important that one of the things we found in talking to 12 local authorities was that they all had 12 different sets of policies and priorities. And therefore, deciding to recommend to you what might be the right answer might be completely the wrong answer for Paul there. And we found that when we looked at some of the delays going around the city wall in York. And I said to Andy Fellman, who was operating, and you've got a big delay there. And he said, well, that's because I want it to be. I want to throttle that down. I don't want all the traffic going around. So I think we've stopped at we'll identify where the problems are and what they are and quantify them. And somebody said about the art of traffic management. I think we'll leave that to the artists, the dark art.
Well, actually, I'm not seeing another hand shooting up, and finishing on the dark art would be quite neat. There's another hand.
Good question. You mentioned that you see higher frequency data. How do you source that? How is it different from the standard?
That's our secret.
No,
No, so genuinely, sorry, I jest, but we source it from all sorts of different providers. So you know, our core business is data aggregator. That's kind of how we originated. You know, we purchase large amounts of data sets. We work with OEMs, we work with fleet manufacturers, telematics devices, you know, insurance companies, whatever it may be, anywhere that we can essentially get GPS-based data. You know, we are predominantly a road-based company, so we do collect road-based data, but there are plenty of other data sources out there. It's just who has the high fidelity, high frequency that we need, and we actually have a team of people that essentially source that data specifically for us.
Just to add to what Bradley says, I recall sitting in a screen watching the first floating vehicle data box in the country moving around, and it was pinging once every 3 minutes where it was. And I said, oh, one day this might come every minute. And we're now looking at perhaps once a second, and it will get better and more and more. And what we're doing is getting the tools in place that when that tsunami of data starts coming. Yeah.
Tsunami of data. On that note, I'm going to say, could you take your microphones off? And thank you very much to Alison.
Can I just point out that INRIX has paid for the lunch, and there are spectacularly good sausage rolls here. So if you do enjoy the sausage rolls, then thanks very much, Jeremy.
Right. Thank you.